And so today we're only gonna have two talks, and then the rest of the day is for working groups. And first speaker is someone whom you've who's visited IMPA several times. Are always happy to host him and squeeze as much out of him as possible. And that's of course Yuval Perez. So we're gonna have two lectures by him during the workshop, one today and the other one on Thursday. And I don't think that Yuval needs much of an introduction, but just not to let it at that, let me say that his work in many different areas of probability and also theoretical computer science, game theory, combinatorics has been an inspiration to many of us. And it's not only the results, but also the working style, highly collaborative, while the choice of problems, I guess I'm saying I'm a fan. So without much further ado, let us have Yuval talking about gravitational allocation of points on the sphere.
How is it now? Good. Good morning. It's always a pleasure to be here. Today I'll talk about gravitational allocation mainly as a method for bipartite matching that we can analyze. But before getting to the talk itself, I want to just show you a few examples of competing matching methods. So here we have blue and red points. In this talk, I'll always have the blue and red points on a two-dimensional manifold of area n. It will either be a torus or a sphere. You could do other manifolds. It will be about the same. But the fact that it's two-dimensional is important. The nature really changes. The nature of the problem changes in higher dimensions. In fact, it's easier in higher dimensions. So two dimensions turns out to be the most interesting case. So here you see actually the optimal matching of these blue and red points, optimal in the sense of the minimal length. And there's a well-known method, traditionally called by Kuhn the Hungarian method, but we now know it was discovered 100 years earlier. So anyway, what you have on the right is one of the methods that we can't quite analyze. This is the electrostatic method, where red and blue points are, say, positive and negative particles. Reds attract the blues according to the electrostatic potential in two dimensions. And reds, of course, repel other reds. Blues repel other blues. And the points move until they are matched. So here's a little movie of how that goes. So let's see. So we have the blues and reds initially. So green is when the blue and red meet, they become one green particle. Note that when the blue and red meet, their charges cancel. So the point becomes neutral and it stops attracting other points. So eventually we get a matching. And analyzing how far the points travel in this matching is an open problem. There's a closely related gravitational matching, which we are able to analyze, and I'll talk about in the talk. But the electrostatic one is harder, and it's still open. Yes, the speeds are not the really correct ones, because otherwise you wouldn't see what's going on. So they've been artificially, artificially changed so you could see. So up to a global time change, it's the correct dynamics. Okay, so we go back to the talk. Okay, so this is joint work with two really fantastic interns, Nina Holden from MIT and Alex Jai from Stanford. This is a good opportunity to remind those of you who are students and those of you who advise students, that we have a internship and student visitor program at Microsoft, and these are two of the real stars that were in that program. So here is another picture. This one, should say the previous one was done by Patrick Naksung. This one was done by Ander Holroyd. It compares, we have more points here, about 300 blues and 300 reds. And here is the optimal matching, optimal in the sense of minimal average length. On the left is the greedy matching, which is also known as the stable matching. So greedy, I remind you, just take the blue and red that are closest, match them up, then take the next pair, match them up, and so on. And it turns out it's the same as if you think of each blue ordering the reds according to distance. So it prefers to be matched to the reds. Each red, it prefers to be matched to the closest red. Each red orders the blues also according to distance and prefers to be matched to the closest blues. And then there is the notion of Gale-Shapley stable matching, for those who know it. And in this case, it coincides with the greedy matching. So that's why it's called stable. So analyzing the average length here is another open problem that I want to emphasize, and I'll come back to it during the talk. So the optimal matching is, one can obtain it by an algorithm. This is known as the Hungarian method, which is order n-cubed operations. We'd like to understand the performance of somehow faster methods, and we'll see one today. So before going to matchings, we'll discuss the closely related notion of an allocation, of a fair allocation. So a fair allocation will take our manifold, again, either a torus or a sphere. Mostly later we'll work with the sphere of area n. So that's Sn2 is a two-dimensional sphere of area n. It's not the square of anything. It's just two-dimensional sphere of area n. And so we're going to have L will be a set of n special points. We'll call them stars or centers. And these stars will induce some partition of the sphere, which is given by this function psi. So psi will map the sphere to the set of stars with some measure zero set thrown to infinity. But almost all points on the sphere will be mapped to a star. And the pre-image of every star will have the same area. So that's what's called the fair allocation. Here is an example of one of my favorite allocations from a long time ago, joint work with Ander Holroyd, Chris Hoffman, where, so this fair allocation was obtained as follows. So you see this stars here are the points. Each point grows a ball at unit rate around it and captures all the area it reaches first. So if we would just do that, we would get the Voronoi cells. But it stops when it gets its quota of area. So it records how much area it has obtained so far. So you see some points are lucky like this one, and they just obtain area around them. Some points have to go quite far before they are sated. So if the point is hemmed in like this one here, you see it's surrounded by other centers. So it starts growing, but it only gets a small area here, so it keeps growing, and then it kind of comes out here for air, and it gets the rest of the area out here. So this will create territories that are disconnected. We have some partial analysis of how far points have to go here. It's an open problem to understand it completely. But it turns out that this method of gravitational allocation I'll describe next is both more beautiful and more efficient. So, and it has some history. So the new work I'm describing is on this method for random points in 2 dimensions. But there's earlier work I'll come to which motivated this. Anyway, if you get the notices, you may have seen this picture. So, so these are the domains in gravitational allocation, which I'll explain now how it's obtained in a moment. So actually what we'll want is not just an allocation for a specific set of points, but an allocation rule, right? It maps every collection of points to an allocation. And then we would like the distance between x and its image, the star it's allocated to be small on average. So how does this allocation, how is this allocation, the gravitational allocation proceed? So we're going to use a two-dimensional gravitational potential. So you might remember that in 2 dimensions, the radial harmonic function is a logarithm. Now here we're working in a sphere, which is a two-dimensional object, inside R3. We're still going to use the two-dimensional potential log, but this distance, absolute value, is not the distance along the sphere, it's the radial distance. It's the distance in R3, okay, between the 2 points x and z. So z will be a star. We sum over the, so this is the gravitational potential at the point x, this sum of the logs. And then we're going to look at kind of a force which is minus the spherical gradient of this potential. So if you look at the potential at the point x and take its gradient vector, this will generally point inside the ball somewhere. But we want a movement on the sphere, so we take the gradient and project it to the tangent plane of the sphere. So that's what's called the spherical gradient of the potential. Okay? And then we have an ordinary differential equation, a dynamical system, which says at any point, so this is this yx of t. It starts at x, and the derivative at time t is just this function f, the at yx of t. So this is exactly gradient flow or gradient descent for this potential. I call this f the force, but beware that the force here doesn't determine the acceleration of the particle, but rather its velocity. So this is sometimes called Aristotelian dynamics because Aristotle thought that force and velocity are related. But in fact, if you want a physical picture, then if you have a very high viscosity medium, then indeed the force kind of determines the velocity. Anyway, mathematically, I hope this is clear. This equation has a well-defined solution until some stopping time, which is a singularity for the differential equation, which corresponds to the particle being swallowed by a star. Now, one of the results we prove is that indeed almost every point has a trajectory which will reach a star. So there's still some measure zero of points on these boundaries. In fact, these boundaries are piecewise smooth. And on the boundaries, what happens to the particles? They might move inside the boundary, but their movement, they can't move to inside either domain. So what is important for later is that the force is parallel to the boundary for a particle that's in the boundary. Okay, so it's not, so we will use that later. Any question about this dynamics? I mean, this will be like the main player today, or this morning, so please.
Not about this, but about the previous one. Was the electrostatic one also Aristotelian dynamics?
Yes. If you do Newtonian dynamics, then you would have particles starting to circle around stars and all kinds of stuff, which is we don't want here. So, okay, so every star has a basin of attraction, the points that converge to it. And here is the first fact, which is, I think, shocking the first time you see it, is that the areas of all the basins are the same. So unlike the case of the stable allocation I told you later, we don't put any rule that says, that forces the area to be one. Somehow, just this definition and the divergence theorem, as we'll see, imply that the areas are the same. And this is not just for random points. This is for any n stars that you put on the sphere. And the analogous thing holds for any manifold. The areas will be exactly the same. And that's formally new in this setting, but it's not really a new result because this kind of result has been obtained in other settings before. But still, I'll tell you something about it. Here is a little picture of a little piece of the potential, how it looks like. So think of this as a little region on the sphere, and over it we have this potential defined. So it has these singularities at the stars. And you can think of the dynamics, if you want, as by if you have a point, put a pebble at that point and see which singularity it will, which of these holes it will roll into. That's the same. So just a quick little story. So I was giving a version of this talk in Montreal in the Math Congress of the Americas, and the organizer was very careful because he had only 5 plenary talks. He wanted to make sure that the abstracts make sense. So when I sent him the abstract, he said, well, wait a minute, I don't believe your statement. You have to explain it to me before I can publish the abstract. So I first sent him, I sent him this proof, but he really wanted to understand some examples. And so now you get to see them too. So he asked, what if I have one star in the North Pole and it's surrounded by other, it's hemmed in, surrounded by other stars. How can it get its fair share? And somehow the answer is that it gets actually points from quite far away that somehow travel between these stars where the force is balanced, and it gets equal area. And then he said, well, wait a minute, but what if I have one star in the South Pole and all the rest are in the Northern Hemisphere? Surely this one will get a bigger portion. And it doesn't. So even points here that are closer to the South Pole than to the North Hemisphere will get attracted north because these points on the north gang up and pull points up. But this is, won't work for just any old potential. It really is a property of the proper two-dimensional potential on this sphere. So this is the, one proof by formulas I want to show you. So hang on, it's just advanced calculus and just the divergence theorem. So we want to understand why the basins have equal area. So, take one of the basins, the basin of Z0, and write the divergence theorem for the potential U. So actually for the gradient of the potential, which is minus the force. So remember, the force was minus the spherical gradient of the potential. So if you take the divergence of the gradient, you'll get the spherical Laplacian. So this is what's written here. This is the spherical Laplacian of the potential. And this integral over a basin should equal the integral of this gradient of U, which is minus the force, times the outward normal integrated on the boundary. Now, the right-hand side is just 0 because, as we said, the force on the boundary is parallel to the boundary, so it's orthogonal to the unit normal. So the right-hand side is 0. On the left-hand side, you have to be a little bit careful because the potential has these singularities at the stars. So this you have to interpret as the distributional Laplacian. And when you do that, what's the Laplacian of log? So if you were in the plane, the log is just the green function. The Laplacian is just the Dirac at the diagonal at. So the Laplacian this is Laplacian in the variable x. So z is fixed here. So the Laplacian would just be a Dirac measure at z times a constant 2 pi. But because we're on the sphere, there's actually a curvature term. So again, this is just calculation of derivatives. And you get 2 pi times this Dirac minus 2 pi over a. So let's call a the area of the sphere. Eventually, we want to set a equals n. But now it's clearer if we call these variables different names. Okay, so this is a calculation, the Laplacian of the log. So the Laplacian of the potential U will just be a sum of these terms over all the stars. So you get 2 pi times this sum minus 2 pi n over a. Again, stop me if there's any questions. Now, as I said, the right-hand side is 0, so the left-hand side must be 0 as well. So when you integrate this over a basin, there's only a single star in the basin. So you get, from this integral, you just get a 2 pi term, because there's a single star. And from this term, you'll get 2 pi n over a times the area of the basin. So that's it. This equation, you can solve for the area of the basin, and it's exactly a over n for each basin. So again, I'll say something about the history later, but here is kind of the real theorem we prove, is that the expected distance traveled from any point x is, until the star it flows into, is order root log n. So where is the randomness here? You can take any point x on the sphere, then throw down the n stars at random. So the previous discussion of equal areas didn't depend on the distribution of the stars. They could be anywhere. But now we're going to really put the stars uniformly at random. And then with that assumption, the expected distance traveled is bounded, it turns out, above and below by root log n, constant root log n.
So this is similar to the root log n that we saw yesterday?
Yes, and it's not an accident. So this, in fact, there's a close relation between allocations and matchings, and in particular, that relation implies that you cannot get any fair allocation which is better than root log n in 2 dimensions. So I'll explain this later, but here is just some pictures of how these allocations look. So this is for n equals 15. You see the basins are still kind of roundish. As n grows, the basins get a little more elongated. You see this is 200 and this is 750. So it's kind of amazing. You can see the root log n, although it grows very slowly, you can see it in this picture that these domains, these salamanders get thinner as n grows. So a bit of history. The first paper of this nature was a beautiful work by Fedya Nazarov, Misha Sodin, and Volberg in 2007, where they didn't think of gravity. They were looking at, wanted to really understand the distribution of zeros of a random analytic function. So this is, so there turns out there's a unique Gaussian analytic functions. I'll write it down. So, which has a translation invariant zeros. So some ak z to the k over root k factorial, where ak are complex, normal, 0, 1 independent variables. So again, each ak, you make it an independent Gaussian variable in 2 dimensions. So the real and imaginary part are both independent normals. And then you look at this series, sum from 0 to infinity. And here's a beautiful fact that the zeros of this function have a translation invariant distribution in the plane. And this you can find from looking at the covariance function of this. And by the way, Misha Sodin has some beautiful survey articles, and I even have a little book with Ben Huff, Manju Krishnapur, and Balint Virag about zeros of Gaussian analytic functions if you want to find out more. That's another nice subject, but they were interested in understanding the zeros. So given this, so this is the function f of z. So you can write a natural potential, so log f, and there's this correction term. But basically log f, if f is analytic, log absolute f is harmonic. And this is, and they had to use this correction term. And then with this potential, which you don't see gravity, but you see a harmonic potential with, again, it has singularities at the zeros of f, because that's where the log. So with this potential, they did a similar analysis. It turns out that the zeros here are very rigid, so the domains don't get elongated at all. And they could do this in the whole plane. And they analyzed the distribution of the distance that a particle travels in the gradient descent of this potential. And this was the inspiration for later work. So I have a paper in Annals Math with Shurav Chatterjee, Ron Peled, and Dan Romick that does the 3-dimensional Poisson points. And again, one can do it in the whole space directly. You can also do it in so it's 3 and higher dimensional. So you can do it in, say, a d-dimensional sphere and rd plus 1. That would work as well. And but the 2-dimensional random points are more volatile, so you can't do it in the whole plane. The force doesn't converge. So I always had a plan to go back and look at this, and this is what we did in the present work in 2-dimensional. Yes.
All of these settings, the areas of
The volumes are always the same. Yes, yes. So actually, the underlying principle that the volumes should be the same goes back to a paper with a different goal by Caragona and Moser from 1990. And the basic idea is that you should use potentials whose distributional Laplacian are the difference of the two measures. The initial measure, which in this case is a uniform measure, and the target measure is the empirical distribution on the points. So if you use a potential whose Laplacian is this difference, then you have a chance to get equal areas. There's still something to look at per case, but this is the idea goes back, as far as I know, at least to 1990. Okay. So how is this related to? So I will sketch for you the reason for. So I remind you that our main theorem was that the expected distance in the allocation traveled from a point to its target is root log n. But now let's assume that and see how it can be used to get a good matching. So what we're going to use it is now to get a matching from red and blue points. So we'll have n red points and blue points uniform on our manifold, so on our sphere. And we're going to look for a matching with small distance traveled along the matching. And what we want is a matching which is the expected average distance is constant root log n. Now, by this theorem I mentioned before of Aitai, Komlos, and Tusnadi, that's optimal. So the optimal matching is of order root log n. And this is, okay, they proved it in the square, but the proof works equally well on the sphere. Okay, so that's a statement. So let me explain how we get from the allocation to the matching. So we're going to do actually an online matching. So we're going to put the blue points down. They will be the stars. The red points will arrive one by one. They will be moving particles. The blue points are never going to move. Okay? So we throw down the n blue points, but they'll be matched. Okay, so these blue points define a gravitational potential. They are the stars. Now a red point arrives. Think of it as a particle. Oops. A red point arrives, and it feels the force from all the stars. And with probability, again, the red point arrives at a uniform point. So it won't land on the boundaries. With probability 1, it will land inside some basin, and that means it will travel to one of the stars. So that's our definition of the matching. Okay? We remove both of these, the red and the blue, and repeat. Now, okay, so we repeat. We're going to take a second one, and so on. Now, why will we be able to analyze this? Maybe a more natural scheme, which doesn't work as well, is throw down the first red point and match it to the closest blue point, right? Kind of online greedy. The problem is when you do that, then you are biasing your collection of remaining blue points, because the blue point with a large Voronoi cell is most likely to be matched in the first round. And now, after you do that, the collection of blue points gets biased in a bad way. And if you keep going, it's more and more biased, and it doesn't behave well and very hard to analyze. Here it's completely uniform. So the first blue points to get matched. So I expect it to be worse asymptotically for large n. But we can't prove anything about either the greedy. Okay, we can prove something about the greedy. The online greedy, no one has proved anything about its behavior. So that's another challenge. So again, online greedy, you put a blue point, it gets you put a red point, it gets matched to the closest blue, repeat. Very natural scheme. Analyze the average distance. Hasn't been done. Here we do something which sounds similar, and it sounds harder, right? We put the red point, we apply this gravity, we see where it's matched. But this one is analyzable, and it turns out to be optimal up to constant. And again, so the red point gets matched to the blue point. Now, because of the equal area theorem, we know that each blue point has equal chance to be removed in the first round. So we start with n uniform points. We remove one uniformly. Then we have n minus 1 independent uniform points. That's a little easy exercise. So then we can repeat. So these are n minus 1 points, but they're on a sphere of area n rather than n minus 1. So the root log n result is for n points on a sphere of area n. If we have a sphere of different area, we have to scale by the ratio of the radii, which is square root of, in this case, square root of n over n minus 1 won't matter, but, and we repeat, this will matter. So we just keep going, putting in points one by one, and what we'll get is, when we are left with k points, we'll get root log k. I just put the 1 here to take care of the case where k equals 1, but we'll basically get the root log k, and it's multiplied by a scaling factor root n over k, because we have k points on a sphere of area n. The root log k is for a sphere of area k, so you have to scale. Since we're looking at distances, you have to scale by the radius, which is square root of n over k. So you just get this series, which is easy to bound. So for instance, if you just bound the log k by log n, and then you take it out, then you get a really elementary series, and you'll see that this is order root log n. And this is, up to constants, the right answer. But this means two things. One is this means this matching is optimal up to constant because of the AKS theorem. And second, it means that you cannot get an allocation scheme which is really better than root log n, because if you would get. So note that although we talked about gravity, all we used is the fact that we have these fair allocation schemes. So if we had any other abstract fair allocation scheme which had better behavior than root log n, you could apply that scheme to get a matching. Right? So I said I put a point and see where gravity, but I could say, given a fair allocation, I just put to the blue points, I just put a red point, see which basin it's in, remove those, and repeat. So if you had any fair allocation that gave better behavior than root log n, you would get a matching better than root log n, contradicting the AKS theorem. So root log n is optimal. Again, up to constant. Now, this matching algorithm has a feature which is both good and bad. So it's online, meaning, or semi-online. So the blue points are there to begin with, but the red points arrive one by one. So when I decide where to match the kth red point, I don't need to know where the future red points will arrive. So one drawback of this is that this is very badly behaved if I'm interested in maximal distance traveled, because when I have only one blue point left, then the last red point arrives at a uniform point, and it will travel a large distance of root n, basically the diameter of our manifold, before it gets matched. But these last few long trips don't matter that much in the average. Most of the trips will be, of the right order. So for the average, this is fine. For the, so the online necessarily costs you in terms of the longest edge, longest travel. Yes?
Can you optimize this by somehow permuting the red points and throwing them in basically randomly, or is that not going to give any?
No. Now, the right way to optimize this is to use the electrostatic matching. So why are we doing this online rather than somehow putting all the n red points together? Because if we do it together, then two red points are likely to fall in the same basin, and then they will both be thrown to the same blue point, and we won't get a matching. So that's why we put them in one by one to ensure a matching. But if we do the electrostatic version, where we just add repulsion between particles of the same color, then we could do two variations. One is what I showed you in the movie, where the blue and reds both move. You could also do electrostatic where the blues are pinned, can't move, but the reds are attracted to the blues and repel each other. If you do that, you can put all the reds in at once, and it will create a matching, because even if two reds are initially attracted to the same blue, they won't reach it at the same time, And the first red to reach the blue will cancel the charge, and then the other red won't see that there's a point there at all, and it will go somewhere else. So this seems nice both in theory and practice. The problem is we can't analyze it. So the key to the analysis here is that the points that are applying force are in their initial distribution, in the uniform distribution, while the particles that are moving are not applying any force. But in the electrostatic versions, then the red points that are moving are repelling each other. And after a while, we don't understand what is the distribution in space. So we don't really understand the distribution of the force. And so we can't analyze it. But again, in simulations, electrostatic behaves great. So it seems to have better constants than the gravitational. But we can't prove anything about it. So I mentioned to you the greedy case. So in the greedy case, in 2009 with Holroyd, Pimentel, and Schramm, we published an estimate on the distribution of the distance traveled by a point. And when you integrate that, you get that on the sphere, the average distance is bounded by about n to the quarter. So note that we're talking about a sphere of area n. So the diameter is root n. So n to the quarter is a non-trivial bound. But I conjecture we have a heuristic that suggests the answer should be log n without a square root. But this is just a heuristic, and it's open to determine what happens for greedy. So this is not online greedy. This is just greedy where we put all the blue and red together, match the two closest blue and red, and repeat. For the online greedy, no analysis has been done at all. So in the remaining time, which is what, 12 minutes, 15 minutes, I want to sketch for you the reason for the main theorem of root log n, and tell you another surprising thing about the time to get absorbed. Okay, maybe I'll say this last thing first. So it turns out that if you take a point and look how long till it gets absorbed, this is a random variable which has exactly an exponential distribution with parameter 2 pi. So I'll explain this in a little bit. But right now I want to explain the main theorem, which is the expected distance traveled in the allocation. So to do that, we have to understand the magnitude of the force at a typical point. So if we look at the force, of course, if there's a star very close, then that will dominate the force. But most points are not very close to a star. So let's look at the typical point and see what is the force acting on it from the global distribution of stars. So this force is a random variable, and it's by symmetry, it's mean zero. So it's not going more likely to be attracted to the right or the left. So the magnitude is really given by the standard deviation of the force. So we have to compute the second moment of the force acting on a point. So given a point, let's divide the sphere into spherical rings around the point. So here is one such ring at a distance k from some target point y. Now, we want to understand the distribution of the force from this ring, actually the variance of the force from this ring acting on the point y. Now, we have n points in area n. This is, if we look in a small region, this will be approximately a Poisson distribution. So if I look at the small region of area 1, so here I take this ring and I divide it into small regions of area 1 each. So in each of these regions, the number of points that fall, I'm throwing n points in area n, so this is binomial n 1 over n. It's approximately Poisson 1. And so we have a Poisson 1 of points falling in here, and they're applying a force on y. And remember, the force is, this is two-dimensional gravity, so the force is 1 over distance. So the derivative of log. So that's the magnitude of the force, but we're interested here in the second moment. So we're going to compute the second moment. And The second moment is going to be order 1 over k squared, because this is a variable of typical order 1 over k, but the number of these 1 over k factors we have is Poisson 1. So when you compute the variance, you'll go and get 1 over k squared. This is the contribution from each of these regions, and you can add this up over the ring to get that because these are very approximately independent, and so you get that the variance in the whole ring is going to be 1 over k, because in each such region you get 1 over k squared, and this is a ring of area k, so you're going to get the total variance from the ring is 1 over k, and now when you sum over k, you're going to get log n. You have to be a little bit careful. You don't want to sum all the way, because later things, the curvature of the sphere starts to play. But log n is a very benign function. So if you just sum, say, until distance root n, where you're still in the flat part of the sphere, you're still already going to get a log n. So the variance of the force is a log n, and from this, there's some more calculation to do to look at force moment as well, to see that the typical magnitude of the force is indeed root log n. So you have a variable whose it's actually approximately Gaussian. So there is actually a central limit theorem here. So the force acting on a point is approximately Gaussian with standard deviation root log n. So let's look at the point x and see what's going to happen to it when it travels with this velocity. So it will start moving. Remember, the force is typically root log n. Occasionally, a star will move it a little bit, and eventually, it will get swallowed by a star. Now, when will it get swallowed by a star? So remember, the particle is moving with this global force of root log n. The root log n comes from the faraway stars. And when will a nearby star be attractive enough to deflect it? Only when the force from that local star overcomes the global force. Now, the global force is root log n. The local force is 1 over distance to the star. So that's why we drew this strip. For a star to be decisive, to swallow the point, it has to be within distance 1 over root log n from the path that the particle is following. And so if we draw this kind of approximate strip, then the particle will keep moving in that strip until it encounters a star. But if we have a process which is essentially a Poisson 1 process, how long do we have to go in a strip until we encounter a point? Till the strip accumulates area of order 1, right? That's when we are expecting a point. If the area is too small, unlikely to see a point. If the area is much bigger than 1, it's likely that there was already a point there. So that's why we're going to go a distance of about root log n before we encounter a star. Okay, and then a star that's close enough to swallow the particle. Okay, any questions? So this is a heuristic. I want to give a somewhat more analytic. So this heuristic was our initial motivation of why we expected the root log n besides the AKS. But here is something closer to the actual proof. So let's look at psi of x is where x is going to be sent. And just integrating the defining differential equation, we get that psi of x is x plus the integral of the force along the path. So to determine the distance between psi x to x, or to bound it above, we have to bound this integral. So, well, to bound an integral, you have to bound how long is the interval of integration and how big is the function inside. So the function inside, we already said, this is the force. It's typically of order root log n. So we have to understand what is the time. Until now, we've ignored the time variable in this dynamics. But now let's look at the time. So it turns out, as I hinted before, the time is of order 1, and indeed, it has exactly an exponential distribution. And that means that this whole integral will be indeed of order root log n, because the integrand is root log n, tau x is order 1, so you'll get the root log n. Um, so this is roughly the reason for the exponential distribution. So it comes from a beautiful theorem of Liouville, here stated in a more generality than Liouville would state it. But so you can find in Arnold's book on the mathematics of mechanics, you can find an explanation of this Liouville principle. So it says if you have a smooth flow applied to a region omega, and you want to see how the volume of the flow behaves, it's going to grow, and it satisfies the following differential equation. So if we differentiate this at some time, so here we're just starting the flow and seeing how the volume is growing, the derivative of the volume is going to be the integral of the divergence of f. So this is the flow induced by some function f in the same way as we are doing here. So dy dt is f of yt. So this is a very general theorem, and again, classical. But this is this general differential equation. In our case, it leads to the exponential distribution. So remember, our force is minus the Laplace, the spherical gradient of u, and we look at the set Et, which are the points that are swallowed after time t. So note that this set doesn't include the singularity. So on this set, the flow is completely smooth. And then the Liouville theorem, when you write it down, I'm going to go through this quickly, but when you write it down, you get the differential equation for V, which is because of the nature of the potential here, it will just give you the differential equation for the exponential. So again, I'm going through this part a little bit quickly. The corresponding paper with all the details is on the archive. So if you want to see more, you can find it there. So there's been a parallel interesting development started by a work of Parisi and co-authors in 2014. So they were interested in matchings also, but they were looking at the W2 distance as opposed to W1. So instead of average distance traveled, they look at average of the square distance traveled. Now, both Aitai Komlos Tusnadi analysis and our analysis shows that the average square distance is going to be log n, order log n, both for the optimal matching and for the gravitational matching. So I showed you the root log n, but this, in fact, we can analyze any moment. So the kth moment of the distance traveled, we're going to behave like root log n to the k. So, but they were interested in a sharper thing, in the constants in front. And let's focus on the two-dimensional case, which is what we're discussing here. So the average distance squared in the optimal matching, they conjectured with some physical heuristics that it's going to be 1 over 2 pi times log n. Now what's most relevant is their heuristics were based on linearizing the Monge-Ampere equation, and when they did that, they basically got the same equation that we were analyzing here. So again, this is a non-rigorous physics paper, but very fascinating connection. So one, what? No, yeah. So by now, both 1 and 2 are proved. Yes. 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 So again, they did a non-rigorous linearization, which led them to essentially the same equation we were looking at. But again, it was not, it's like a 4-page paper, certainly very creative, but very far from rigorous. But then there's a amazing work by Ambrosio Strat-Rebizan, late November 2016, which actually establishes this 1 over 2 pi in 2 dimensions. In the process, they lose the exact matching. So they don't prove that gravitational allocation has this 1 over 2 pi. but because they use a duality argument. So in the duality, so they emphasize we don't find what any explicit coupling that will achieve this exact optimal. So they don't prove this suggestion that this will be something like this gravitational or Laplacian type matching, but they do prove that the optimal matching will have this asymptotic 1 over 2 pi. And that leaves us with the conjecture that indeed the gravitational scheme I showed you, although it's not optimal for any fixed n, when you drive n to infinity and look at square distance rather than distance, the conjecture that arises from combining all these predictions and works are that that should be have the optimal asymptotic constant, so this 1 over 2 pi. But it's still a conjecture. Here are some pictures of how this looks in the hyperbolic, how the gravitational location looks in the hyperbolic plane. This is from work in preparation by Jian Ding and Ron Peled. And I want to end with recalling the conjectures I mentioned, so about the electrostatic matching. So that is the most attractive target to analyze, but it also looks hard. Again, there is the greedy matching, both online and offline, which seems like they should be easier, but we don't know how to analyze them as well. Thank you.